Welcome to this tutorial video. Today, we will explore the I2C communication protocol, a very popular peripheral in embedded systems. Let's take a quick look at the history of the I2C peripheral. I2C stands for Inter-Integrated Circuit, a data transfer protocol developed by Philips Semiconductor, now in XP Semiconductor, in the early 1980s. I2C communication is designed to enable data transmission between integrated circuits on the same circuit board. The main purpose of I2C communication is to minimize the number of connection wires and support connecting multiple devices on a single bus. I2C communication has become a popular protocol in the electronics industry due to its flexible connectivity and cost-effectiveness. Below is the connection diagram of the I2C protocol. It consists of a master and an I2C bus. On each bus wire, a pull-up resistor is required. We will learn more about these pull-up resistors later. On this bus, you can connect many devices such as sensors, I/O expanders, RTCs. Each device has its own address, so only 2 wires are needed. You can also connect multiple masters on the I2C bus. The SD and SCL pins of the I2C bus are configured as open drain, an important specification of the protocol. With a normal GPIO, it has 1 PMOS and 1 NMOS, allowing easy control of high or low voltage. But with open drain, the GPIO lacks the PMOS, so the pin only drives low, while the high state is floating and needs an external pull-up resistor. This prevents conflict when multiple masters are connected. As mentioned, since GPIOs are open drain, pull-up resistors are necessary. Typically, the value is around 4.7 thousand ohms. They provide a path for SD and SCL to return to high after being pulled low, preventing floating lines and ensuring reliable data transmission. I2C supports different communication modes. The most common is standard mode at 100 kbit per second. It can go up to 3, 4 bit per second, though not many microcontrollers support such high speeds. Below is a basic transmission frame of I2C communication. It includes start condition, address byte, read-write bit, ACK, NACK bit, data bytes, multi-data bytes, stop condition. First is the start condition, the first signal on the I2C bus. It's defined by SDA goes from HIGH to low while SCL stays HIGH. This alerts all slaves to listen for an address byte. Next is the address frame. The master tells all devices which slave it wants to talk to. The address is 7 or 10 bits long. Each device must have a unique address. The master uses this to communicate with the slave. The read-write bit is the last bit of the address frame. It tells the slave if the master wants to write 0 or read 1. Example, slave address equals 0 by 30. Write 0x31, 0 equals 0x60. Read 0 by 31, 1 equals 0 by 61. After sending the address, the master floats SDA. The pull-up resistor pulls it high. If a slave exists, it pulls SDA low. The master checks SDA voltage to detect a CK low or an ACK high. If the master receives a CK, it continues with a data frame. The frame may contain the register address, configuration values, or commands. After the data frame comes an ACK signal, just like the address frame. Finally, the stop condition. The master generates stop by SDA goes from low gives high while SCL is HIGH. This ends the transaction, frees the bus for other masters, and sets the bus idle.